So it's 9 o'clock in the morning Central Time here in Houston. And let's start this meeting. So some of you might know that Professor John McLennan is traveling right now to Norman, and I will stand for him and will moderate this meeting. It's a bi-weekly ARMA seminar organized by ARMA Hydraulic Fracture Community, for which John is chair and I'm co-chair. And as usual, the seminar lasts for 1 hour. We'll aim to have 15, at least 10 minutes at the end for Q&A. And after a short introduction, I will give floor to speakers. So today, I'm very pleased to announce that we have two distinguished speakers. Let me give a short introduction. So the first speaker is Dr. Yves Guglielmi. I hope I pronounced his last name correctly. And he's a geological staff scientist at National Laboratory at Lawrence, Berkeley. His principal interests include fundamental research in hydromechanics of fractured and faulted rocks. He's focusing on in-situ understanding of complex relationships between hydraulic, elastics, and strengths properties, as well as rheology and geoseismicity of faults and fractures through various field observations. Applications of Yves' research concern giant rock landslides, geoenergy, which includes nuclear waste disposal, reservoir seal integrity, and deep geothermal energy. And he's been principal investigator of several national and international programs on CO2 storage in deep reservoirs and on giant landslides in European Alps. Our second speaker is Dr. Mark McClure, who is widely known for his company he established in 2015 called Microfrac. And the mission and objective of this enterprise is to help operators maximize value through applications of advanced geomechanics and reservoir simulations based on proper physics and constrained by proper data. Before founding Microfrac, Mark was an assistant professor at the University of Texas at Austin in the Department of Petroleum and Geosystems Engineering. After earning his bachelor degree in science in chemical engineering and master of science in petroleum engineering from Stanford University, Mark earned his PhD in energy resources engineering at Stanford. I should also add to this that Mark was very generous with our community by sharing very frequent and very insightful blogs on his company's site. So thank you for this. Let me ask everyone to mute their microphone. So I don't have control of this. So I'll just need to ask people to mute. And with that, so Yves, Mark, so I'd like to give floor to you. Yeah, please aim to leave a little bit of time for Q&A at the end.
All right, well, thank you everyone for attending today, and thanks for hosting today, Alexei. I'll be starting off the presentation, and then I'll be kicking back and forth to Yves, so we'll be kind of switching off at different points. There's a lot of co-authors on this paper, and that's for good reason. Really, all of the work for this presentation was done by the EGS Collab team. Tim Knifsey is the leader of that, but it's a big effort, a lot of people involved. I'm almost embarrassed that I'm the person presenting it because I've had a very minor role in EGS Collab. It's really all of their work. And also all the SIMFIP measurements and that tool and the deployment were handled by Yves. I'm presenting because I noticed and I pointed out that we could use the data that they're collecting at the project to address the topic of stress measurement. So I personally put this stuff together into this material, but certainly it's all their work. So thank you to everyone in the Collab project for your extraordinary efforts. And here's a full list of the people who performed the EGS Collab project. So it's a long group, and here's a list of the organizations involved in the project. So really remarkable collection of organizations. Here's just one slide of background. So the EGS Collab project, this is performed in a mine shaft. It's called the Sanford Underground Research Facility in South Dakota. This was once the Homestake mine. And there's a variety of scientific research that happens at this location, of which EGS Collab is just one of many. The advantage of this project is it's mesoscale, which means that we are able to do things that are actually in the ground, that are at the scale of real operations. Maybe not quite as big as a true, let's say, DFIT that would be performed in a shale well, but it is in the ground. It's real size, bigger than that could be done in the laboratory. But because these are basically, they're drilling wells off these mine shafts that are a few hundred feet long. And so that means they can drill a lot of them. They have a tremendous amount of data collection that's taken place. There's been, multiple microseismic arrays and cross borehole, active, passive seismic, and on and on and on. Just a huge amount of data collected to allow really, really high fidelity characterization. And one of the pieces of data that's been collected is what Yves calls the SIMFIP tool, which is, as we'll discuss a little more later, a tool that is taking direct strain deformation measurements during fracturing and after fracturing. So there are different phases of the EGS Collab project, and we're going to use data from two different phases of the project here. We're going to call the quote 164 tests. So those were performed in May 2018, and then there's the 4100 tests performed in October 2019. So those are actually performed in two different sections of the drift of the mine shaft. So Yves, would you like to discuss the SIMFIT tool?
Oh, yes. We had the opportunity in that Collab project to upgrade the SIMFIP tool that I'm going to describe here. I would say the main thing we did within that project is we were able to upgrade that tool to a very high operating pressure. You will see the values, but the Collab experiments take place at about 1.5 kilometer. And at this depth, we are trying to do some fractures stimulation or hydrofractures. And the injection pressures are about, let's say, between 20 and 30 megapascals. So the challenge was to upgrade that tool that we continuously develop to these pressures. So what is the tool? You may see a schematic map of the tool in the middle of the slide. Basically, it's a hydrofrac straddle packer. You see the packers P in black in the middle of the slide. And we just, if I may say so, added between the two packers three-dimensional displacement sensor. How does this work? Basically, the displacement sensor is attached to two anchoring points, which are named A and B in the slide. And for example, the tool initially was dedicated to capture direct three-dimensional displacement of natural fractures. So you could imagine that you just set the anchoring on both walls of the fracture, like it is shown in the upper right. And then you seal the interval with the packers and increase the pressure, stimulate the fracture, and then measure the relative displacement between anchor A and anchor B. Just to mention the specificities of the tool, when this central three-dimensional displacement sensor is anchored, it is free to move relative to the sealing system. I mean, relative to the packers and the straddling tube, which is connecting two packers. So that's specific to this probe. It's kind of floating then, and really measuring only what's happening about the rock. How does it work? Basically, you may imagine that the key element is what you see on the upper right. It's a cage with what we call 6 wings, which allow to measure strains in 6 different directions. And so when A is moving relative to B, the cage is deforming. And because we measure deformations in 6 different directions, we are able to reconstruct the relative three-dimensional displacement of point A relative to point B. The strain measurements, just to mention, are made because there are a bunch of these using fiber Bragg gratings mounted on one single optical fiber. So this tool can operate very deep actually, because there is no electronics. It's just based on strain based on optical fibers, so we can operate in deep wells. The lower graph is showing an example of a measurement. And I will come back to this in the next slide also, because this was one of the measurements that we are going to use also in that talk. I think, Mark, if we switch to the next slide, I have I can explain also the same thing. You know. So this slide is just to illustrate the tool. So you have a photo of the tool in the surf gallery, ready to be deployed inside one of the testing boreholes. So you see the borehole in that case was an inclined borehole. So the tool can operate vertical in any direction, you see. And you see the packers, maybe, sorry, I don't have the mouse, but you see the black zones are the packers. And in the middle, I'm sorry, you don't see much because, of course, the displacement sensor is protected. But you may imagine there is a lot of metal in the middle, which is aluminum mainly. And this is where we had the three-dimensional sensor. And below is just an illustration of a test and test results that we can get with this tool. For example, on the left, we are targeting that fracture that you see that we identify thanks to an optical log. And we are going to set the tool across the fracture. So you have the size of the chamber, which is in that case about 2.4 meters long, which is the blue rectangle. And the anchoring zone is a little smaller inside the chamber. The upper anchor and the lower anchors correspond to where I figured the red lines. But you see in that case that we managed to anchor the tool across that fracture, which initially was a hydrofracture. And the test here was about reopening a hydrofracture, okay? Then in the middle, we just conducted what I would call a classical hydraulic test. We increased the pressure by small steps until we reopened the fracture. So you see that the pressure is the red graph, and we increase the pressure step by step until we see an opening, and the opening is characterized by the drastic increase in the injection flow rate, which is the blue graph. So you see, for example, if you go into details, that this is happening at point B. You see these vertical lines, and we will shut in, sorry, the chamber at point D. Then there will be a small shut in until point E, and then we will step down the pressure in the interval from E to F. But before, just pay attention that, as usual, before the drastic increase in flow rate, before point B on the graph, and starting at point A, you may see that the pressure steps are not staying at steady state. So we may think that starting at point A, there is some kind of reopening of the fracture, but not yet a huge one. So it's not really seen on the flow rate. And so these points actually also corresponds to key points that we can see on the three-dimensional displacements. So here, just imagine that with the tool, we are able to do a continuous monitoring of the displacement, and you will see such curves in the following of the talk. But here, for sake of simplicity, I just took the displacements at point O, A, B, C, D, and it makes a bunch of displacement vectors. And these displacement vectors are projected in a stereographic projection, which is shown on the right, where you also have black curvilinear projection of the hydrofracture. So the hydrofracture you see here, it's called HF in the graph, is dipping steeply to the south, okay? And you see how the vectors evolve during the test, let's say from OA, then AB. Remember, AB is when we start seeing transient variation of the pressures. And then BC is when you have the huge increase in flow rate. And that's very interesting here because you see AB, the vector is plotting almost on the trace of the hydrofracture. So it means that in that case, we mainly are measuring a shear or tangential displacement on the fracture. And when the flow rate is drastically increasing, when there is vector BC, you may see that the point has migrated to the north, and above the label BC, you might see a small, sorry, it's not so visible, you might see a small black dot, you know, two dots, one inside the other. And this figures what we call the pole of the fracture, which is the perpendicular to the fracture plane. So it means BC migrated perpendicular to the fracture plane. So thus it means that at BC, the fracture mainly is opening. So that was a bit long maybe, but just to explain what we can get with this kind of measurement. Mark, I think you can, it's you now.
Okay, all right. All right, perfect, thanks, Yves. All right, next slide. All right, so our objective here today is to look at the interpretation of closure pressure, or actually more accurately, the interpretation of the magnitude of the minimum principal stress, SH-min, from shut-in pressure data taken from fracture injection tests. And we're going to compare data from fracture injection tests with data from the SIMFIP tool measuring the deformation. So here's just a movie of a fracture injection test. Here we're injecting right now. We're going to create this fracture. You can see in this case, it has a confined height. And when we shut in, the fracture will start to close. Here we can see it progressing through the transient plots, and we'll see pressure spreading out around the fracture as time progresses. So the idea is we're going to inject at a sufficiently high rate to create a hydraulic fracture, shut in, and then interpret that shut-in transient to estimate the magnitude of the minimum principal stress. Here is the challenge. There are a few different proposed procedures for estimating the magnitude of the minimum principal stress from these measurements. So it's very common to plot pressure versus G time, and the G function is a function of shut-in time. It is somewhat equivalent to the square root of shut-in time. And I have three different methods for estimating stress shown here. So on the top, I have this big control bar. I don't know if you guys see that. I'm not sure how to get rid of the control bar. Here we go. Hide floating meeting tools. There we go. So this is a paper written in 1987 by Castillo showing a plot of pressure versus G time. If you identify the deviation from linearity, that was taken as an estimate for the minimum principal stress. So I would say that's the classic method of estimating stress from shut-in transients. Certainly still used in rock mechanics, geophysics, fields like that. So you can see it in the Mark Zobak book. You can see it in rock mechanics literature as well. In 2009, and this is when the paper came out, I think this method was used prior to 2009, Bari et al. Wrote a paper proposing to make plots of pressure versus G time. That's the blue line. And then they recommended making a plot of the derivative, dPdG, multiplied by G. So that G times dPdG is this red curve here. And then they recommended drawing a tangent from the origin to the top of that curve. That's taken as the point of quote closure. And so you read down, you identify the pressure at that point in time. That is the stress estimate that they arrive at. So that is a different method. Now, one thing that we should note is when we perform microfrac, or rather defit tests in shale, very often this is a horizontal wellbore and there's a large near wellbore tortuosity that develops. So in this particular plot here, which is real data, we can see that the actual pressure at the moment of shut-in was above 11,000, but within just tens of minutes, it had dropped down to closer to 8,300. So we're going to not believe that the fracture in the far field had a pressure of 11,000. What we think happened is there was a nozzling between the well and the far field fracture. So the far field fracture during injection was somewhere down here around 8,300 PSI or so. If we were to use the Castillo method on this data and ignore the beginning of the transient, deviation from the straight line would occur around here at a much higher pressure. So we can see that this tangent method is different from the Castillo method, or rather the deviation from straight line method. So in a series of papers over the several years that I've written with a variety of people, Mukul Sharma, Dave Kramer, as well as Alexei was part of our DFID industry study, and several others, we've proposed a procedure that we're calling the compliance method, which is actually the same as the Castillo method. And so the idea here is we're going to plot the derivative. Instead of G times dPdG, we're just plotting dPdG. Identify the point where the derivative reaches a minimum, and then as it lifts off that minimum, that's taken as an estimate for when the fracture walls have come into contact. The contacting of the fracture walls is increasing. The stiffness of the system causes the increase in the derivative. So this is where the walls have contacted. Then based on numerical simulations, we understand that contact pressure is slightly higher than the minimum principal stress. And when we fit numerical simulations to real data, that's about 75 PSI higher. So the compliance method is to take that point, subtract 75, and that is the stress estimate. So these are very different. I believe in this data that I've plotted here, these two methods are about 400 PSI different. It's pretty substantial. And when we look at net pressure, the difference is something like 200 and 600. So we're talking about a 3x difference in net pressure from the two methods. And so if we want to do hydraulic fracture modeling and things like that, of course, net pressure determines the size of the fracture. So it's a large discrepancy. Now with further work, oh, you know what? I need to change the title of this slide. This is not the right title, but again, what is the premise of the compliance method? You can show that the derivative dPdG, the red curve there, that's equal to the rate that fluid leaks off divided by the system storage coefficient. And so when the walls are out of contact, the system storage coefficient is the wellbore storage plus the storage coefficient of the fracture itself. When the walls contact, the fracture becomes stiffer. That CT term drops. That's why the derivative goes up. So, and this mechanism here, what I'm showing is a numerical simulation and also field data. So we can make numerical simulations that lie right on top of field data. This is a simulation that goes all the way from the beginning of injection to late time. And we could do that, with a physical model that captures this process of fracture walls coming into contact. And as the walls come into contact, there's a residual aperture. The fracture has some roughness, but that roughness allows aperture to retain open partially, and you switch over to a joint closure law, and the fracture aperture kind of non-linearly asymptotically approaches zero as pressure falls off more and more. Now the monotonic decreasing dPdG is an important wrinkle in this discussion. So on the right here, this is a DFIT done in the Bakken shale. And you can see that there's really not a point where dPdG hits a minimum and comes up. I'm not going to count that as anything meaningful right there. And so this is seen in a substantial percentage of tests. And so, I just explained mathematically why I think the derivative is supposed to go up when the fracture walls come into contact. That doesn't always happen. I'll just skip ahead one slide to say how often these things happen. So this is a paper that I wrote a couple of weeks ago, or I presented a few weeks ago, reviewing 62 DFIT shale DFITs we've done. And what we see is that about 59% of them had what was categorized as a strong compliance response. In other words, there's clearly a very good S shape on that dPdG plot. Another 20-ish% was categorized as adequate, where we do see a minimum and a come up, but it's not as strong. And then roughly 18% of those 62 were categorized as having no indication, shown here. So it's certainly not the majority, but it is certainly present in the data. I will also note that when you do microfrac tests, smaller volume tests, you're more likely to see this type of behavior. And I'll talk about that in a moment. So what is happening here? We need an interpretation of this. And I think it's a little bit less well understood than perhaps this signature, which we fortunately see in the majority of shale DFITs. But when we've performed numerical simulations, the best explanation is the fracture has closed very rapidly. So basically, if you have a high permeability, if you have a small crack that's leaking off into a conductive natural fracture, if you've pumped a large volume and then you come back later and pump a small volume, all of these processes can result in a situation where the crack is only barely open during injection, and it's essentially closing very quickly. So an interpretation of a test like this could be that the fracture flows very quickly. And so rather imprecise, we could say that the stress is somewhere around here. One more wrinkle, if this is a horizontal well, and in fact, this data was a horizontal well, we do know that the near wellbore tortuosity elevates the derivative at early time. So if we had very rapid closure simultaneous with near wellbore tortuosity, it would be ambiguous what the stress estimate is. So in fact, the actual compliance procedure in this paper here, 2019, is that if it's a horizontal well and we have the monotonic DPDG, we simply do not make an estimate for stress. And if it is a vertical well or otherwise a situation where we understand that we don't have substantial near wellbore tortuosity, then we interpret it as being, quote, rapid closure. So this is a little bit less satisfying, I think, than the very clean compliance interpretation. Also, it's less precise, but this is the best that this method, these authors with myself being obviously one of them, are putting out. All right, so now let's move on to how do we differentiate. So again, I mean, the main puzzle here is that we have two different methods, or let's say three different methods that can yield a 3x or more difference in net pressure. Not always, but often. Sometimes, I will also point out that sometimes these methods are closer together. Sometimes they're only 100 PSI apart. If they're within 100 PSI, I think that's the experimental error of something like this. So it really just depends on the data set, how different they are. So let's say that we have measurements, direct in situ measurements of deformation versus pressure. So this is something that we'll take from the SIMFIP, and I'll show a few other examples here in a moment. How would we and how should we estimate the minimum principal stress from data like this? So this is a figure that I have kind of imitated from Golrodani and Nolte's chapter in the Reservoir Stimulation 2000 textbook, which is a really excellent textbook. So I kind of traced over the line. This is their schematic from the In-Situ test that was done in the mid-90s, showing normalized displacement versus pressure. What we see here is, and this really is a plot that could be made during injection. So like this could be a reopening plot, or it could also be a shut-in plot. Actually, reopening may be a little cleaner in some cases because it's happening fast and there's less poroelastic effect. So the point of this plot is that there's a linear period up here. This linear period is where the fracture is opening a lot with only minimal increase in pressure. And that is straight from linear elastic fracture mechanics, the idea that the aperture of a crack is proportional to the net pressure. Net pressure divided by stiffness, or net pressure multiplied by compliance. And of course, this stiffness and compliance depends on the fracture geometry and the modulus, et cetera. So that's what is describing. This equation here describes this straight line period of the plot. And we can readily say, what happened here? So this is the quote contact point. That's where the fracture walls are coming into contact. Now I often hear, well, the crack kind of closes progressively tip to center. What I've seen in my modeling is that, yeah, there's a little bit of a tip to center type closure, but then the lion's share of this sort of displacement happens after the entire contact has happened everywhere along the fracture. So let's say this is where the fracture is starting to come into contact. I would say maybe here the fracture is in contact everywhere across its face. There's still a lot of aperture left over because of the roughness of the fracture, and it takes additional normal stress to crunch down on those asperities. And when people talk about quote full closure, I don't know what full closure means. To me, contact across the full fracture walls, that is a well-defined thing. But to say full closure is a very ambiguous term because, as you can see, the aperture will never really go to zero. It's just going to asymptotically approach zero as pressure goes to negative infinity. But anyway, back to the topic of what is SH min. It's the x-intercept. So if we were to say this equation describes this straight line, then there's only one value that's possible for SH min that can be a point on this plot, and it's right here. That's because if we look at this equation, when pressure equals the normal stress on the fracture, or SH min if it's a hydraulic fracture, that's when W bar equals zero. So it's quite straightforward that when we make a plot of displacement versus pressure, identify this straight line, extrapolate it down to the x-intercept, that is SH min. I think that's almost the definition of SH min. All right. So there's a few other papers that have looked at this sort of data in the past, and I'll go through them quickly here before we go on to the SIMFIP data. This is from Duttler et al. This was performed at the it's a project in Switzerland, forgetting the name, sorry. They have a series of microfrac tests that were performed, and they took extended shut-ins. So like shown here, here's pressure and G times Z PDG versus G time. And then they actually have, not exactly like the Simfit pool, but they also have offset wells with deformation measurements. And so they see, just like we showed here from Golrajani and Nolte, we have a plot of pressure and deformation. They're creating a straight line, taking the x-intercept, and they're developing stress estimates from that. So in this case, the test is about 4.5 megapascals. Well, here is a G times Z PDG plot from that data set. And what it's showing is that even as pressure is getting down to 2.5 megapascals, which is down here, the G times Z PDG plot is still going up. There's no indication of closure from the tangent procedure. Now, he also discusses there's not really a DPDG deflection in most of their tests. So most of these Butler tests were essentially in this monotonically decreasing DPDG regime, probably because they're small little hydraulic fractures that are leaking off quickly into natural fractures. So from the perspective of the scale of the problem, size of the crack, the conductivity of the natural fractures, it's kind of acting like a fairly high permeability formation. And so actually, basically that 4.5 would be about right here. So this crack essentially closed very soon after shut-in. Here's an example. This is actually the same data that is plotted in that reservoir stimulation textbook. This is a plot of normalized tilt versus pressure. In this data set, this is from the IMSITE data set. There is really a very distinct pressure. It's remarkable how just sharply pressure, or rather tilt, begins to increase. That is at about, whatever it is, about 24.5 megapascals. If we take the pressure shut-in data from right before, this is a reopening test. This is the shut-in data from immediately before it. And here I'm using G times the PDG. The deflection upwards in that corresponds to the point where the derivative is increased. So a compliance pick is right about here, right at about 24.5, exactly where this is located. The tangent pick comes in later. It's more down about right here. And then here's a reopening test. This is a microfrac test done in a vertical well with an MDD tool. What we see here, it's 2 cycles, and the G times Z PDG plot has been made for the shut-in data. So they've plotted these red dots here and here. Those are the estimates for stress from the tangent interpretation. And I would argue that the reopening pressure does not appear to be here, right? So I would view that while reopening pressure could be seen as something that is a little bit ambiguous to define, my interpretation would be it's up here somewhere, and there's really no apparent deflection when injection pressure reaches this point. In fact, really, what's happening is something closer to the ISIP is a lot closer to the reopening pressure, and so this is another test where we have a monotonic DPDG and just a rapid closure response is the best interpretation. So that's my lit review. Oh, and the last one I didn't mention is this Broker Ma paper that came out just last month at the Pedretto site. And they also, actually, they had some tangent method interpretations that were like half of the other methods. They didn't just use compliance, they used some other methods that are more commonly used in mining. And what they found is even if they assumed a frictional coefficient of 1.0, they would still find that the rock was not in frictional equilibrium because if they use the tangent interpretation. So there's a lot of literature out there. I've obviously, I have an opinion on the topic. My view is that the literature is consistent in showing that these tangent interpretations are not accurate. Now, I've picked out the worst examples. There are other examples where the tangent interpretations are similar to methods like this one or this one. But I don't know of any data set where the tangent interpretation is right and the compliance method is wrong. So they're either the same or the tangent method is wrong. That's what I've seen in the literature to date. So here we have a new data set to look at. We have 4 microfrac tests with extended leak off and with SIMFIP measurements. And so I'll let you pause, Yves, and sorry I've gone on, we're talking too long, but I'll let you go ahead and Yves and discuss the SIMFIP measurements, and then we can talk about the rest of the data.
Thanks, Mark. So here I'm showing the first 2 tests that, as Mark mentioned, were done that we call them the 164 measurements or test in EGS Collab. So the rock is a metamorphic rock, and you may see on the lower right a schematic setting of the test zone. Basically, there are two boreholes. There were much more actually, because there were monitoring boreholes which are not shown here. Inclined about 10 degrees to the north, and an injection borehole and a monitoring borehole. The target of that first experiment was to create a fracture from the injection borehole and eventually to grow the fracture until it intersects the monitoring borehole. And actually, this experiment was highly successful because we managed to do that. As Mark mentioned, the big EGS Collab group, and not only Mark and me. But the thing is that there was a SIMFIP probe in the injection borehole to monitor the initiation and the propagation of the hydrofracture towards the monitoring hole. The distance between the two holes, if I remember, is something like 10 meters. And what I am showing on the right is we have several lines of proofs that give us a kind of insight of the orientation of the fracture that we created. What you see on the lower right is, for example, there was a seismicity monitoring, which corresponds to all the colored points, which are seismic events. The colors are varying because it's depending on time. Okay, the color means the time, whatever. The blue mainly is what's happening at the beginning, and the red at the end. And so you see that at the beginning, until it's bluish or yellow, the dots kind of align or match into a plane, a rough plane, of course. That's the first argument to say that they could correspond to the plane of a hydrofracture. Other arguments we have is that we know where the hydrofracture intersected the monitoring borehole, and that's the black point, which is figured as INT that you see. So you see that if you compare the alignment, the fracture from the alignment of the boreholes and the alignment of the seismic events, I mean, and where it intersected the borehole, it's not so bad. So again, it's another argument to say that we have a view maybe of the fracture that was created over the 10 meters spacing of the two boreholes. And now in the injection borehole, you see two curves. I will not give details of the purple one, which is a modeling of the SIMFIP signal. Let's just look at the red one, which is the raw SIMFIP displacement during the stimulation. And you may see that, okay, it starts from the borehole, and then it goes down until a point, and then it goes back almost perpendicular to the fracture plane. So when it goes back, the point when it changes direction back to the fracture, it's when we shut in the injection. So it means that we have a nice shut-in. The shut-in in some cases was, for example, during step 2, it was overnight. So it's a very long one. And I think that's the one we are going to discuss in the next slide with Mark. Why? Because there are other reasons. If you, I don't want to go too much into details because we could talk quite a lot on this single test. But the SIMFIP shows that during an initial step before we completely grow the fracture towards the other borehole, actually the experiment was done in 3 steps. A very short initial step, which was just to initiate the fracture and lasted a few minutes. Then we stopped and shut in the interval. Unfortunately, there we had a problem, a technical problem during the shut-in, so we could not use it with Mark. Then the second step where we grew a little more the fracture, we say we try to glue it to 5 meters. Of course, that's a, a rule of thumb idea, which is step 2. And then the step 3 that I'm not showing, that I'm showing as the 3D view, where we completely glue the fracture until we intersected the monitoring borehole. So obviously for the study today, the most interesting step is step 2, because at this time, we grew the fracture, but we did not intersect the other borehole, and we went sufficiently away, I would say, from the near borehole influence. And the near borehole influence, the SIMFIP showed that there is kind of a reorientation of the SIMFIP signal from what we see during the first step, that you may see, for example, on the left, compared to what we see during the second and the third step. For example, if you compare the middle graph with the graph on the left, both graphs are showing in plan view the SIMFIP displacement. And you might see that the SIMFIP displacement, for example, if you look at point A, first is going in one direction, and then it's changing direction. And then there is the shut-in, which is the orange part of the curves. So when we analyze of that, to be short, and sorry, I don't think I'm short at all, we think that during step 1, we initiated the fracture along a borehole defect, which was a foliation plane. And it initiated through a kind of a sliding along that foliation plane until it went away and reoriented certainly towards stress to create the macro hydrofracture that we see connecting to the other borehole in step 3. So the shut-in in step 2 is very nice, I think, because if you look at the direction of the hydrofracture, which is figured in dashed lines in the middle graph, you see that the shut-in has an initial part which is exactly perpendicular to the fracture, and a final part which is doing something more tangential or more different, I would say. And I think we were very interested with Mark in working on this part on the entire shut-in. And Mark, please go ahead.
All right, thanks, Yves. And I'll mention there's 2 papers on this topic that are really good. One is by Yves, and the other is first authored by Ping-Ching Fu.
But there are 3 papers. There is also one by Martin Schoenbull. There are 3 papers on this. That's right.
Yeah, the Schoenbull, and those are good because they really explain the argument for why it's a hydraulic fracture. I'll mention a couple more. There aren't a lot of natural fractures with this orientation, and also there's a sewer cam that's run in the offset well, and the fracture intersection does not correspond to a natural fracture that's already intersecting the well. So it all lines up for a hydrofracture. All right, so here are plots of the displacement from the SIMFIP versus pressure. The blue is the shut-in data, and the black is the reopening data. And then I guess the moment of shut-in is the intersection of the blue and the black. So in test 1, the very beginning of the data is complex because we're not only kind of sliding this foliation, but need to actually initiate and reopen. So this is not really interpretable. And unfortunately, as Yves alluded to, there were some data problems where we lost recording. And so we can't necessarily use the blue curve, the shut-in curve from test 1. Test 2 is definitely the cleanest. The reopening and the shut-in, they lie right on top of each other. Now, when we talk about the x-intercept, I think it's possible that there's a little bit of, it doesn't have to occur at 0. It should occur where the kind of final asymptote is. But anyway, the final asymptote here is very close to 0. So if we draw the straight line through this period, in both the reopening and the shut-in, the closure, we land at about a 21 megapascal normal stress on that fracture. That's also the stress at which we see the fracture reopen in test 3. So I think we have a really, really good stress estimate here of about 21 megapascals from this data and from this data as well. Looks like we got a red line from somebody. I don't know how to get rid of that red line. Sorry. All right, so 21.4 megapascal is about 3,100 psi. That's obviously a little bit imprecise, but it's somewhere in that ballpark. All right, so we have two shut-in transients. We have a short shut-in transient from test 1 and a longer from test 2. So the pressure measurements lasted a little longer than the SIMFIP, but they also went out. There was a power outage in the mine, but we have a very long shut-in from test 2. So first, let's look at test 1. And here is the dPdG plot, and here is the G times dPdG plot. The dPdG plot from test 1 shut-in reaches a minimum and comes up. So in terms of a compliance method interpretation, it's very straightforward. We would say something about right here is where the derivative has increased a significant amount from the minimum. We would come up here and say that this roughly now is when the fracture walls have contacted. If we subtract 75, we would land on 3,100 psi. So the test 1 compliance interpretation is about 3,100 psi, which is just about what we are getting from the SIMFIP also. Here is the G times dPdG plot, and what it's showing is that the curve is still increasing when the test ended. So the pressure got as low as 2,900 psi. G times dPdG is still going up. So we can't really tell what the tangent method estimate would have been. We just know that it would have been something less than 2,900. So in this case, just a straight up comparison, we're seeing that the compliance method worked really well. The tangent method came in low. The test 2 transient is not quite as ideal. In terms of the dP to G curve, it's really just monotonically decreasing. We don't have this sort of nice deflection that we're seeing here. I don't want to say that that's an increase. Again, I mean, if the test had gone on longer, I don't think that the derivative was increasing here. But so this appears to be a monotonically decreasing dP/dG. So we would interpret that as a rapid closure. And so again, that's a very imprecise thing. But the compliance interpretation would be that the stress was somewhere up here, because we do not think that there is a near-well tortuosity effect. The G times dP/dG curve is still increasing at the end of the transient. So here is G times dP/dG. It's clearly even deflecting upwards. So the tangent interpretation of this data would have been evidently substantially lower than 2,200 psi. So 2,200 psi is way below the 3,100 estimate that we're getting from the SIMFIP. It's basically saying that the tangent method would have been somewhere down here. So it's really inaccurate. Now, I will give one caveat to this data. There is an indication that there was a small amount of fluid that flowed into an adjacent observation well that was grouted. And so that potentially had an impact on the test. And we cannot really say for sure what that effect was. So I think that's worth mentioning that. This is known because there was a DTS in the offset well, and it showed a small little signature that suggested probably some fluid was getting into it, which could have been from the fracture hitting that observation well. But point is, in these two tests, while they're not the same, because this one appears more monotonic dP/dG, they are kind of consistent with our interpretations and the compliance procedure, and the tangent method is coming in lower. All right, so then we have two more tests in the 4,100 drift. And Yves, we're getting tight on time. We need to leave time for questions.
Yeah. So sorry for everyone.
It's my fault too.
No, very fast. I'm showing another way of how we can analyze the SIMFIP data. Here you have the optical log in that other place. So we are not at the same place. We are a little shallower. Mark, it's 300 meters less or something like that, I guess.
So this is a different part of the mine.
Yeah, it's a different part, but anyway, it's about the same rock, let's say. The difference in this test is that the borehole, as you see on the log, is initially fractured. The zone we are testing has some natural fractures, which are apparently sealed with calcite of silica, but anyway, there are fractures. And in the middle, you see the before and after image of the image log. Not very spectacular. We just see a stronger contrast along one pre-existing fracture. That's the only thing we see after our SIMFIP stimulation, which makes us think that maybe here we just reopened or reactivated the natural one. And actually, on the lower right is again the view of the SIMFIP vectors at initiation and and then at opening. I made it very simple here because I anticipated we would not have any more time to explain, sorry. But you may see that it could match very well with that natural fracture that initially was a little shared, the red point, and at opening, it was a kind of a pure opening of that natural fracture. And the interesting point here, if you compare that natural fracture with other tests done in the same borehole, but this time it was in intact zones, and we were able to see clearly a hydrofracture test, and that's the upper right graph. You see our natural fracture has not exactly the same orientation compared to the hydrofrac that were created. So we may think that that SIMFIP test shows that we reactivated the fracture, maybe not so well or not so optimally oriented versus stress as would be the hydrofracture that we observed in borehole.
So Yves, in this test, you talked about the same thing, but then the hydraulic fracture formed off the foliation quickly. I mean, what is your interpretation on this test? Is it possible that a hydraulic fracture could have formed off this natural fracture away from the well, and would you have detected that with the SIMFIP?
I think that's really possible, Mark. The only thing here is that we have in this test we only have one borehole, you know, and the SIMFIP is seeing much more, you know, but the SIMFIP is not enough to make an interpretation and say, okay, then away from the borehole we are seeing. What we can see, and I think I wrote it, the second line, you know, clearly we see what I would call a far field effect, you know, during the shut-in and after we see some SIMFIP signals that do not match by the simple opening and closing of that natural fracture I'm seeing here. But and I could define a direction from that, but that would deserve to be proved by other measurements, I would say. For example, if we had some induced seismicity. But yes, clearly, Mark, there is a far field effect, which is not clearly related to that near field natural fracture activation.
Sure. All right. Yeah. Oops. Sorry, I got mixed up here. All right. So I'll pull up the SIMFIP. We'll try to get through this.
Yeah.
So what we're seeing here is you know, the injection data is quite non-monotonic.
Yeah.
Would you like to talk through it quickly, Steve?
Or I think given the time we have, we just say that you clearly see that the signal is very complex here, and obviously it shows that there is a near field borehole complexity, and it's even complex during the shut-in actually. And you see the onset of the far field effect. You know, it's going down to zero, and then there is a rebound coming after. And that's typically is something coming from the far field.
Okay, so that may be an indication of that reorientation. So this is unfortunately a little more ambiguous, right? So that's not as clear cut. The minimum point of displacement in both of these tests is at 19 megapascals, which is about 2710 to 2785 psi. So that's something we have to work with here, but we know something else was going on. All right, so if we look at the pressure transients, here's the dPdG plot, a very clean, what you would call a compliance signature. It goes down into a minimum, it comes off the minimum. And so if we did the compliance method, we would get a stress estimate of about 2475, which is actually, you know, a few hundred PSI lower than this minimum, more closer to here. If we use the tangent method again is just still deflecting upwards at the end of the shut-in. So we reached again about 2200 PSI. This was the overnight shut-in, and they had to move on with the project. So the tangent method says that the minimum principal stress is something less than 2200 PSI, and we don't know how much less it would have gone. So again, I'll just go quickly for time. This is less certain. Based on what Yves done is he looked at the orientation of this natural fracture, and he said if a hydraulic fracture had formed off of it, that was perpendicular to SH min based on what we see about orientation, that would imply that SH min magnitude is 2567. Obviously, there's not that many sig figs for real, but interestingly, that is in the ballpark of the compliance interpretation. So one possibility that is not as strong is that that actually a hydraulic fracture formed off this natural fracture. The fluid pressure is transmitted through the natural fracture out into the hydraulic fracture. And so the compliance method may be picking up that stress estimate. But again, the tangent method is coming way lower than that. So I'll just skip ahead if that's all right, Yves.
Yeah, please go ahead. Yeah.
Okay. So for test 7, so this is another one in the 4100 borehole. Here we can look at the shut-in data. There's the straight line period. We can draw a straight line, come down here and get to about 18.5 megapascals, which is about 2680 psi. Also, we have a flowback after the second cycle. It also comes in at about 2700 psi. So we think the best estimate for stress from the SIMFIP is 2700. In this test, if we look at the dPdG and the G times dPdG plots, this is the one case where they're relatively similar. So in this case, the G times dPdG tangent method is at about 2700, and the compliance stress estimate is slightly higher at about 2800. So in this case, they're within 100 psi. They're not too different. And we would see that they're both in the ballpark of the SIMFIP measurement. So this is the one case where the tangent method and compliance were similar. All right, so we'll just pause for questions. Sorry, guys, we went too long and we didn't leave enough. I'm happy to stick around for longer if you'd like. But thanks for listening. Oh, and my dog wants to get involved. All right.
Yeah, to everyone, if I can just add on the last test, the SIMFIP may say that either we reopened a natural fracture which is well oriented versus stress, or we created a new fracture.
Okay, so does it conclude your presentation?
Yes, thanks.
Can we go to Q&A? Okay. Well, a couple of things. Yes, we have 4 minutes to the hour. So, so formally we'll end meeting there. But Mark, you said that you might stay longer for some Q&A. And sure. I don't know if it's available. So we'll continue as long as we go, but formal part will stop. And I hopefully will continue recording a little bit beyond the hour. And by the way, Mark, you might be able to remove this annotation through your end. I send you instructions. I cannot do it on my end.
Oh, okay. I don't think I'm the one that made it.
Yeah, no, but you're sharing the screen and you can remove annotations.
Nice.
Okay, you did it.
Thank you.
Thanks. Yves already kindly answered some questions in chat. Let me pick those which hasn't been answered. I think the first one unanswered is from Anastasia. Do you ignore the well-bore stress concentration when interpret the reopening of for SH mean as SH mean?
Well, if you're talking about the SIMFIP measurements, I mean, again, the goal is to use the straight line period here. And so the idea is that pressure is determined by the normal stress on the far field fracture. Now, if there was a substantial near wellbore tortuosity effect, and the pressure in the wellbore was really different from the pressure in the far field fracture, certainly that would affect this method, but we don't believe that's the case here. So certainly the reopening pressure itself could be affected by the near wellbore effect, but we're not really using the reopening pressure. We're really using the linear extrapolation of the linear period. Okay.
Panos, if that didn't fully answer your question, then please unmute and follow up.
Yeah,
sure. I think it's a good answer. Since we're at the hour, I just want to thank everyone who needs to leave the meeting. Thanks for joining this very interesting presentation. It is recorded and it will be shared later as long as Q&A after the meeting. And for those who are leaving, I just want to remind that hydraulic fracturing community, ARMA hydraulic fracturing community will support one more workshop during ARMA symposium this year. It will be focused on fiber optics data and geomechanics, and it will occur on 26th of June, Sunday, just before the ARMA symposium itself. So the information is on the ARMA website. I encourage everyone to have a look at this. It will be very, very interesting and full of data, as well as analysis. So now we're going to informal part of this meeting, so past the hour. Second question is from Yarlong Wang. He's asking, would you think that plastic zone may exist around wellbore that may affect external or far field stress interpretation?
I mean, I think I would give the same answer I think I'd give the same answer, that we're trying to form a far field fracture that's extending meters away from the well, and so hopefully getting out away from near wellbore effects.
Okay, so it might be there, but it's probably negligible.
But just to add on what Mark is saying, when there is a borehole effect, it creates a complexity in the SIMFIP. You cannot miss it, I would say. and I think it's not a very nice SIMFIP measurement in a way, I would say, but at least it gives you a strong information that you must be careful that there is a borehole effect.
Okay. Next question again from Panas. It's not clear. The statement is not clear, but the derivative after minimum has increased significantly to pick up the closure as it was linearly increasing.
Yeah,
I'm not sure whether. Okay, go ahead.
I guess he's saying, that sounds slightly subjective, and I think that's fair. I think it is a little bit subjective. So I think when I have a mathematical script, like a computer program that does it, it looks for a 10% increase from the minimum number. So that would be one rule of thumb you could use. It would be a 10% increase from the minimum.
In this case, you constrain it by displacement measurements. Go to next question. Ahmad, you may want to formulate your questions in somewhat shorter formats.
Could I just?
Go ahead.
Yeah, it's easier.
That's what I'm saying.
Typing it, and I couldn't type all of it. Okay, so my one of the questions that I have, and I thank you for the very nice presentation. Did you try the reopening pressure for that test one? And then how'd that go?
So the black line is the reopening. You mean the reopening of test 2 after test 1?
No, at 164.1, you had 3 stages of injection. So you had stage 1 injection, stage 2 injection, and stage 3. So was there a reopening analysis done for the pressure from stage 1 to 2?
So you mean the reopening at the beginning of 2 after 1?
Yeah.
Yeah. So that would be the black line here.
Okay.
Yeah.
So that's about 21 or 20.
Yeah,
22, which is
the perceptible change in displacement is obviously a little lower. Maybe that's 19.5. But again, my interpretation would be that's the unloading of a mechanically closed fracture.
But what I was meaning was did you try the pressure profile to get the reopening pressure?
I see what you're saying.
Because that would give you probably a very nice kind of reliable number, maybe. But my comments, which was long, is that, okay, so, y'all are suggesting that you had a hydraulic fracture, during the first injection cycle. And I looked at the data, and that has like 2 liters, I believe, of fluid injected. And so if you do a rough calculation and you assume that your hydraulic fracture is a 1/10 of a millimeter wide, you would need something about around 20 liters to extend that fracture, say 10 meters away from the wellbore. And so the mass balance is not satisfied, it seems to me. And I didn't consider leak off, and there was, probably substantial leak off. So,
I think the idea is that it took until step 3 is when the fracture broke through to the OT well. So the idea is in step 1, we think that the fracture went only at maybe a couple meters from the well. Yeah,
if that. So, but then, so to me, to get a hydraulic fracture, a planar hydraulic fracture, it's nearly impossible because, if you look at the data from the foliations and natural fractures in the injection interval, there are 2 that are dipping in such a way that they would, come and intersect the presumed hydraulic fracture. Or the hydraulic fracture would intersect them. So there is some kind of a complexity going on here that I think it's manifested in the fact that, it's difficult to get a closure pressure in the second attempt.
Yeah, Matt, I think I agree with you. It's a bit more complex than what we're showing here. And for example, Peng Cheng in his paper is showing that maybe there is a kind of relay between 2 hydraulic fractures to get to the monitoring borehole, which are subparallel, with a kind of transition zone or relay zone, which might be relayed through foliation, or we don't know. if you look at the induced seismicity, I said well, roughly it's aligning on a plane, at least I would say at the beginning. I'm talking of the, let's say, the light blue dots, but we may discuss, they're not really aligning, you know. Obviously, some things are happening around, you know, so I completely agree with you that in details it's more complex. But I would say after a while, the signal at the SIMFIP is getting very, very simple, maybe because it's the place where it's wide open, you know, and where you have the maximum pressure. And when you get away from that, of course, you get into complexity, branching with natural fractures and these kind of things in details, I would say. So, yeah, I agree that it's certainly much more complex than what we are trying to show here.
I would say that, you know, the conclusion of the project was largely that this hydraulic fracture was just cutting across most of the natural fractures. There is one large fractured region where the fracture did perhaps terminate and then jog slightly and then reinitiate. But the vast majority of the natural fractures seem to have been no barrier to propagation of the crack.
No, it seems to be a new direction of fracture, clearly.
Yeah.
But we cannot avoid that there has been at least maybe not so much leak in natural fracture, but clearly, as you see from the seismicity, some reactivation around of natural fractures.
Yeah, and the pressure profile, and I don't want to dominate the discussion, you know, and let other people ask questions. And the pressure profile is kind of peculiar too. You know, it sort of, to me, it shows indications of, you know, something going on, because, you know, at some stage, as you continue to inject, the pressure continues to, you know, increase. And one way you can explain that is by some kind of a, you know, tortuosity function or something like that. So something is going on there, but yeah, it's hard to say what. Thank you.
Thanks. And you know, all this data is public, so anybody's welcome to check it out and see what you see.
Yeah, for people, we can give the link if they don't know how to find it. I think all the data are on OpenAI, and you can go to the link of the test we showed. I think if anyone cannot find them, just send me an email and I will try to give you the right link.
Thank you for sharing this help. And you already shared link in chat area. We have one more comment from Panas. Panas, do you want to unmute and ask it, or shall I just read it? No? Then
yes,
please do.
Actually, it's we have a time delay. I'm sitting very long from USA. My question was about the discussion of the closure pattern. So, and the numerical computations with the plasticity model show clearly that the fracture closes in a kind of a zip kind of a pattern. Whereas if you compare with the closure in strong rocks modeled by elasticity, then it closes like a hinge. So it makes contact at the same time. And this, apparently this kind of a closure pattern affects the interpretation of the mini-fracs. This was my comment.
Yeah, I understand that the comment. I'm pulling up a figure from a paper I wrote a few years ago. So you're asking, you know, if the crack had zero roughness and you assumed it was linearly elastic, then the crack would kind of close everywhere at the same time. But that's not necessarily what happens in reality. That's the question.
Yes, it's yes. In wake rocks, it's not the case.
Yeah. So I'll just pull up this this paper. So in the numerical simulations I was referring to, where we match these tests, we assume that there's a residual crack aperture. And so let me just show some figures of that. So here's kind of a zoom in on a crack closing. So the red is the roughness of the crack. Obviously, that's an average roughness across the length of this fracture. So what we're assuming is that once the average aperture at a location reaches 0.5 millimeter, the walls are in contact. So we do see something that's sort of like a progressive tip to center closure like you're describing. And this is elastic. Yes. This is an elastic model, but it's happening because of the roughness, right? So if you have an ellipsoidal distribution, but there's kind of a flat kind of cutoff at the bottom, then you end up kind of getting cut off progressively.
You can say in dilation than roughness. You drop
exactly.
dilation. Yeah.
So in these simulations, what I show, like in this figure here, or maybe I'm remembering, but basically, the kind of period from when it's partially closed to fully closed, like in terms of partially contacting to fully contact, is maybe from like here to here. But then there's still a lot more derivative increase that happens after this point. Does that make sense? Because here there's still 0.5 millimeter of aperture, so the walls are contacting everywhere here in this image, but there's still a lot more closure to happen because the asperities are just barely kind of contacting across the surface everywhere. So I think I see two different things happening. I do see this kind of zipper, like this tip to center thing happening, but then even after that, there's still more kind of joint unloading to occur as the pressure falls off.
Yeah, it's clear. Thank you.
Okay, thanks. Appreciate
very
it.
Nice. Yeah, it's very nice.
Okay, cool.
Thank you, Panos. Maybe last question for me, because there are no more questions in chat. Probably more to Yves. On monitoring fracture opening and closure, so after closure, when fracture essentially becomes a joint, do you observe hysteresis similar to what's is in Barton-Banz's model, this hyperbolic displacements affects the stress relationship? Do you see anything like that, or it's not, or the tool is not sensitive enough to pick up this normal closure behavior relationship? Or you see something different?
It's a great question. Maybe. I mean, do you have a comment on that? I mean, we're measuring, that exact behavior here. So maybe this is worth a look. I don't know that we've looked at it.
Because after closure, it becomes a closed, essentially normal folds.
Yeah, right. So I mean, if we're saying
not a normal model should apply to it.
I think it's a great point. I mean, if we're saying that we think that the crack walls are contacting somewhere like here, and we think the stress is somewhere like there, then we have here an empirical measurement of the Barton-Bandis.
And from there, you can infer roughness of the fracture.
I agree.
Not precisely, but to get some sense of roughness of actual hydraulic fracture.
Yeah. I haven't done that. I don't know if you, but you guys should. It's a good idea.
Clearly, we could. Yeah. Yes. We should.
Idea.
I think. Yeah. That's an idea.
Okay.
Yeah.
It's on OpenEI. You guys should do it.
All right.
Alexei, can I make one more comment? I mean, it's just if nobody's in a hurry. So this is to Mark mostly, and so he argues in his paper, and he didn't mention it today, but he argues that the superiority of the compliance/stiffness method compared to the tangent method is the issue of net pressure. That is, the tangent method would yield a very high net pressure, and so then there is an objection because that could that is deemed unrealistic. Now, to me, the method he's proposing has merit on its own, but this argument, may or may not be, a strong basis because, a high net pressure could easily be justified, based on what we have seen HFTS1 and HFTS2 in terms of the complexity of the fractures or parallel fractures that are present, or maybe segmented ones. So I think maybe a different line of argument would be more convincing in that context.
Yeah, I agree. I mean, that's not something we talked about in this paper, but that is ultimately the crux. I would say that I'll say this. I can't guarantee it, but I'm 99% sure that if I was using, I'm positive if I assumed the stress was 12 megapascals, the net pressure would be humongous, and I wouldn't be able to explain the observed fracture sizes. So actually, when we pumped these tests, I had done a quick mass balance calculation in advance of the tests. I was assuming a few hundred PSI of net pressure, and the crack actually grew faster than I predicted. And they hit the monitoring borehole before my simple calculation. That's partly because I had assumed a symmetric crack, and in fact, the crack was totally asymmetric. I think that's why it was so off. But if I had made my net pressure 4 or 5 times higher than that 200 PSI, we would have not matched this. But I think it's a good point. And I'll say more broadly, in my work with my company, we get data sets now with offset fiber observations. where we can see individual crack hits at 500 feet away, and we know exactly when and where they occurred and how many there were. And the kinds of net pressures we use are a couple hundred psi per crack. So remember, when you do multi-stage fracturing in shale, you might have anywhere from 4 to 20 clusters, and that many fractures, theoretically that many planar fractures propagating at the straight time. And at the same time, as you mentioned, maybe there's really more than that. But what we find is, if each individual cluster had a net pressure of 800 psi, then the aggregated net pressure of 15 to 20 clusters would be, much higher than is really observed. So I certainly, from my perspective as someone that does fracture modeling, I believe that these couple hundred psi measurements are right. And in fact, if anything, fractures are bigger than we thought. There are plenty of cases now, HFTS2 is an example, where the microseismic says the fractures are shorter than they really are, because we have fiber in the well 1,000 feet away in HFTS2, and we see tons of frac hits directly observing the fiber. But the microseismic in part of the HFTS2 well says the fractures went like 400 feet. So if anything, what we're learning from fiber is that cracks are bigger than we thought. And we're having to match that with net pressures of something like a couple hundred psi per fracture strand. That's certainly not in this paper, but that's my observation.
That's a great argument, Mark, I think. Because net pressure comes, if I may just add, it can be important for two reasons. So one is as an implication of these measurements. So it does make difference, as you were pointing out, whether it's plus minus 400 psi interpretation for the design and optimization of hydraulic fracturing treatments. But on the other hand, actual data can be used to constrain interpretation, like you were explaining. And we see that fractures are so big that they should be pretty thin, otherwise we cannot maximum mass balance. And also Kyle Houswaite made the phenomenal presentation at HFTC this month, where they use actual pressure data and stress sharding calculations to bracket net pressure in a particular field, and it was 200 psi.
Yeah, it was 200.
And that's very promising technique. We should get more of this in other basins as well, because it's straightforward to collect this data, and you can very narrowly band your net pressure, and that probably will provide final answer in this debate how to interpret that closure pressure.
Yeah, and Houswaite with Devon, they also have a paper where they've looked at hundreds of wells with serial bore pressure, and they have great stats on fracture lengths. I think that paper's in the Eagleford. I would note, though, from my broader experience, that fracture length is variable by shale play, and so it's not like there's one size fit all answer to this. But usually they're bigger than we thought. Has been my observation lately.
Right. Well, I think we're through all the questions and comments, and 70 minutes all time. And so thanks a lot to both Yves and Mark for presenting this quite unique data set and analysis, and also for staying longer with us to answer additional questions. And I also like to thank everyone for attending this presentation. So the next one will be in 2 weeks from now. John will lead it as usual next time. And with this, we're closing this meeting. Thank you.
Thank you. Have a good day.
Thank you very much.
Thanks everyone for attending and all the great questions. Appreciate it. And sorry we took too long.